Etienne Racine. We'll be talking about work we've been doing together for the last several months. Etienne got his PhD at Cornell, working with Ina Flanagan. He's part of Ina's sort of something taken over Kip's role, or continues his role, producing among the best graduate students in the field. And Etienne is a good example of that. He's been here at Caltech for how long?
Year and a half. Yeah.
He's, I think, nominally working for Inspirals, but I managed to do some.
Yeah. Well, I guess half and half. Yeah. Okay. So the topic of my presentation today is the Gaussianity of Lisa's confusion background from extreme mass ratio Inspirals. And as Kurt said, this is work that I've been doing with him for the last year or so. Now let me just start with some background stuff. So extreme mass ratio events are expected to be a strong source of gravitational waves for Lisa. And these events occur when a stellar mass compact object gets captured by a supermassive black hole at the center of a galaxy. Now what's so interesting about these guys is that they will allow high precision measurements of supermassive black hole masses and spins, and maybe potentially also probe the space-time, the whole space-time structure of those black holes. So there's a lot of interesting things to learn from these sources of gravitational waves. Now, how do we see these guys? Well, a typical Emery waveform has many cycles in it because it lasts for several years, so it's a good candidate for a matched filter search. And what matched filter does is essentially it looks for correlations between the observed signal and a bank of template signals, and you span some parameter space that's tailored to this class of source that you're searching for. And in the case of these guys here, the bank of template has something like, it's 14-dimensional, so it's fairly huge, so you need about 10 to the 35 templates to do that search. Now, if the correlation between the signal and a given template here, so that's the signal, that's the template, is big enough, then you claim that you have seen a gravitational wave that's matching that template and that signal if the correlation is larger than that threshold. Now let me describe what is the definition of the confusion noise for these experiments. So a given signal that is seen contains two major components. One is noise that is inherent to the experiment, and the second component is a background of gravitational waves that you do not know exactly what they are or where they came from, so they're essentially not, what's the word, resolved. Now, so in a matched filter search, this unresolved background radiation acts as a source of noise exactly at the same level as instrumental noise, so this is why it's called confusion noise. And in the case of Lisa, the predominant source of confusion noise is generated by the collection of several millions of white dwarf binaries that are in our galaxy. Now, Barak and Cutler also showed that the unresolved Emerys also contribute significantly to the confusion noise for Lisa. And here's a plot of what is the strength of the confusion noise from black hole captures. So here's the Lisa noise curve with the confusion noise from white dwarf binaries added, and here's the well, if you adopt the point of view that that's the worst case scenario. So this is the strength of the confusion noise from black hole captures. And if you construct the full Lisa noise curve, when you include that extra source of confusion noise, you see that in the region where the Lisa noise curve is the lowest, then the confusion noise here makes a relatively significant contribution to the total noise curve. So it's important to.
So you're using the phrase black hole capture equivalently to Emery?
Yeah, well, it's a small black hole it's a stellar mass black hole that's captured by a big one. So that's what I mean by black hole captures.
Is that what an Emery is?
Yeah, it is, but there's also white dwarfs and neutron stars. So that's only that one class of objects here. Now, in the Barak and Cutler paper, there's a little caveat, and it can be described as follows. So the number of Emerys that are quote-unquote on at a given time can be fairly large, so it can be up to, say, 10,000. And So Barak and Coulter assume that because that number is fairly large, you can use the central limit theorem and claim that this noise is going to be fairly Gaussian. So you can treat it as a source of Gaussian noise for LISA. Now the problem lies in the fact that to detect MREs, you have to set your signal-to-noise detection threshold pretty high. It has to be around 14 sigma. So that's pretty far out in the tail of that of the distribution of signal-to-noise. And so the issue may be that the central limit theorem does not really apply that far out in the distribution, and that the tails of that distribution you might actually need a much larger signal-to-noise threshold in order to confidently say that you've seen a given MRE because of that confusion noise. So basically the problem that we address is, can that background produce a lot of false alarms at 14 sigma, which is where the central limit theorem tells you you have to place your detection threshold. And if it does give a lot of large false alarm rate, how high you have to adjust your detection threshold so that you can state confidently that you see a given MRE. And if it turns out that you have to place it at 100, then, well, it's probably impossible to ever see these guys. So the way that we investigate that problem is to use two tools from statistics. One is called the Edgeworth series, and the other one is something called large deviation theory. Okay, so again, what we investigate is the tail of the probability distribution of the overlap between a search template and a confusion noise data stream, and that confusion noise data stream is composed of a sum of individual MRE signals, which I label H sub j. And so the signal to noise produced by correlating the template and the confusion noise is of that form here. So it's the sum of identically distributed independent random variables, which is what allows us to use these two tools from statistics that I've mentioned before. Now, generically speaking, you're going to have a significant overlap between the template and a given binary in your confusion noise when their frequency is roughly the same. So that's essentially when they happen to cross in the time frequency plane. So that's going to be a picture that's going to come back a bit later in my talk. Okay, so what I want to do now is describe in some detail what are these statistical methods that we use to address this problem. So in the case of the Edgeworth series, what that is it's an approximation to this. Well, it's an extension of the central limit theorem, and so the type of variables that I'm going to consider here are a sum of identically distributed parent variables, which I label here y sub j, and we rescale the summed variable capital Y so that it has a unit standard deviation. The two assumptions that we make here is that, first of all the moments of these parent variables are defined, so the expectation value of this variable to any power exists, and that these guys have zero mean. Now, one can show that the probability distribution for that variable, for that summed variable, is given by this following series expansion. So this is the Gaussian predicted by the central limit theorem, and you have these corrections that you can expand in a power series, where each term is scales like a power of square root of 1 over n. And it turns out that these functions here that makes the coefficients of that power series are polynomials in that variable, and they depend only on the parent probability distribution. Now, one problem with this sort of expansion is generally it's not convergent, but in the large n limit, it gives a good approximation to the true probability distribution if you retain the first few terms. So it's an asymptotic expansion. Now I want to show briefly how where this expansion comes from. So the key quantity that you need to look at in this setting is the characteristic function of your two variables. The characteristic function is just the Fourier transform of your probability distribution. Now, if you expand the log of the characteristic function of the parent distribution, that's called the cumulant generating functional, you get a power series that's of that form. So this is your Fourier frequency, and these coefficients here are called the cumulants of your fundamental distribution, of your parent distribution. Now if you do the same thing and expand formally the cumulant generating functional of the probability distribution of your summed variable, then you can go through these few lines and show that you can express it in terms of the cumulant generating functional of your original, of the parent distribution, but as a function of this rescaled frequency. And so you can see in that way that the probability distribution of your summed variable depends only on the cumulants of your original function, and also on the number of variables you have in your sum. Now if you take the exponential of that last expression, you get this formula here, where you see that the first term becomes a Gaussian term, and you have the following exponential. And now the key part of the calculation is you formally expand this guy in a power series, and you collect terms in powers of 1 over square root of n. And when you do that, you can see that the coefficient of that series are going to be just polynomials in I omega, and that these polynomials will depend only on the cumulants of your parent distribution. So in that sense, this is a very powerful tool, because it allows you to obtain the full distribution knowing only the properties of the parent distribution. Now the last step is to obtain the probability distribution itself, is take the inverse transform. And since these are polynomials in I omega, when you take the inverse transform, I omega just becomes ddy. And so when ddy acts repeatedly on that term in front, you just get that these functions here are going to be polynomials in y. So this is where this expansion comes from. Now again, as I've said before, this is not a convergent expansion in general, but it gives, in the large n limit, a good numerical approximation to the true distribution in some domain of your summed variable, capital Y. Now this property is useful in practice, because you can just say, well, I'm just going to take that series expansion, truncate it to the first few terms, and that's going to give me a good idea of what the true probability distribution is. Now the one real problem with this is that estimating the size of the corrections is very difficult. And the reason is that, again, the series does not converge, and so looking at just the size of the next terms does not necessarily tell you how well the series is doing. And so there's a theorem giving a bound between the difference of the true distribution and the truncated series, but it's not really useful in practice. So I'm going to come back with how we address the size of these corrections a bit later. So for our purposes here, I'm just going to assume that the first two correction terms are going to give a reliable approximation to what the probability distribution of the overlap is. And when you retain the first two terms, you have this expression here, which depends only on the third and fourth cumulants of the parent distribution. And these polynomials are Hermite polynomials. And the corrections scale as 1 over square root of n to the 3/2. But again, we don't know exactly what the order of magnitude is. We only know the scaling with n. OK, so that's one tool that we use. The other tool that we use is called large deviation theory. Now, this is a much more powerful tool, because it is designed specifically to study the large tails of a distribution for a variable of that form here. So this summed variable now is just the average of a sum of identically distributed random variables. And the main result of that theory is that the probability distribution for that summed variable is of the form of this exponential here, where this function is called the rate function, is obtained by this following formula, where this is, again, the cumulant generating functional of the parent distribution. Now what I want to do is just not derive this, but just motivate where this result comes from by looking at how this compares with conventional results from statistical mechanics. So if you think of that summed variable z as being a state variable for some StatMech system, Then in general, there are many microstates, which are essentially the set of the random variables that you draw from their probability distribution that lead to a given value for your state variable. And as we well know from StatMech, then the probability of realizing a state that has this value for your state variable is essentially proportional to the exponential of the entropy of that state. And so this motivates the functional form for the probability distribution. So this rate function is essentially the analog of the entropy. Now, how do we compute that entropy or that rate function? Well, in StatMech, if you say fix a state variable for your system, then the way to maximize the entropy of the system is to populate your microstates according to some thermal distribution, where you fix your temperature to give you the correct expectation value for that state variable. In that case, it's the energy of the system. And so, stated a bit differently, the vast majority of microstates which will give you this value for E are going to be the ones that are populated like this with that value for the temperature. And similarly, when you look at, say, a fixed Z here, the vast majority of microstates that result in that particular value for your state variable are drawn from a probability distribution that is essentially your parent distribution multiplied by this thermal factor, where this parameter theta is chosen so that, of course, the expectation value of your variable gives you the one that you fix. And so this here you can just you can see it's essentially the derivative of the cumulant generating functional of the parent distribution with respect to your inverse temperature parameter. And so once you have found what is the temperature parameter that you have to use for these distributions, then you can compute the value of S. And in StatMech, then this guy is just simply given by the log of the partition function plus the value of the variable you're keeping fixed divided by your temperature parameter. And so this motivates what the functional form of the rate function must be in the case of sums of identically distributed random variables. So it's essentially the negative of your cumulant generating functional plus, so that's the analog of that term here, plus the variable you're keeping fixed times the inverse temperature parameter. So I'm not claiming this is a rigorous derivation of what the rate function should be. I just hope it's some sort of illustration where it comes from. Okay, now what I want to do for the second part of my presentation is to apply these two tools to two toy models of the overlap of a search template with a realization of confusion noise. Okay, so the first toy model that I'm studying is of the following form. So we assume that the overlap between our search template and a given binary in the confusion noise is just a random phase variable times some distance type variable. And the scaling here comes from the fact that the scaling of the gravitational waveform of a binary scales with distance like 1 over d. And so, the origin of this phase term I will motivate a little bit later when I discuss some more sophisticated models. But for now, we just assume that the overlap depends on just these two parameters here. Now, this phase variable, as I said before, is uniformly distributed, and the distance variable is drawn from a probability distribution chosen so that the density of binaries is uniform and that it lies within some sort of shell-like volume. And the reason why we choose such a shell-like volume is because there's a maximum distance beyond which these binaries will not be very important for confusion noise, because their signal is going to be redshifted down at too low frequencies. And so you'll never see crossings with any search template that you're using. And this low distance cutoff is essentially because the binaries that are really, really close to you are going to be extremely loud, and so you can probably see them by some different mean, just maybe by eye, and so you can just take them out of your confusion noise, and that process you can do up to some cutoff distance. And it also turns out that this cutoff distance is important for the cumulant generating functional to be defined. So let's do the Edgeworth expansion for this probability distribution. So what we need is the first 4 cumulants of that probability distribution. Now the odd cumulants depend only on odd powers of the variable x. So because the phase is uniform, then by phase symmetry all the odd cumulants vanish. The second cumulant is the variance, and the fourth cumulant is given by this formula. So it's the expectation value of x to the fourth minus 3 times the variance squared. Now if you go ahead and compute what that is, so this is the square of the variable x, the overlap, take its expectation value, and you obtain the following formula. So here I'm assuming that the cutoff distance is much smaller than 1, where 1 is the size of my volume. Now when you go ahead and compute the fourth cumulant, you get a result that is like this. So it scales as 1 over the cutoff distance. So if you were to take a cutoff distance very close to 0, you would see that this guy diverges, and the Edgeworth series is not well defined. Now when you take these two results and plug them in the probability distribution for the signal-to-noise ratio, what you obtain is the central limit theorem times our correction term. And if you look at the 14 sigma tail, which is where we're interested in that probability distribution, you obtain that the size of the correction is roughly of order 10 to the 3 divided by the number of binaries and also divided by the cutoff distance. So what that means is that if you keep your detection threshold at 14 sigma, you have all these extra events that would claim to be MREs, but in fact are not. So what we need to do is just adjust our detection threshold so that we keep the false alarm rate at the constant value that is determined by setting your original threshold at 14 sigma if you assume that your distribution is exactly Gaussian. And when you compute what this new location of your detection threshold must be in that toy model, it turns out to be only at 14.3 sigma. So it's a very, very tiny change in what your detection threshold should be. So it seems to indicate that the effect of the non-Gaussian tail is pretty small in that, at least in that first toy model. Now, however, again, the problem is that we do not know exactly what is the size of the correction. So all the terms that I've dropped in that power series, exactly how big they are at 14 sigma. And so this is why we use large deviation theory to confirm that the Edgeworth series actually works reasonably okay at this value of the signal-to-noise ratio. Okay, so for the large deviation analysis, what you need to compute is the cumulant generating functional for that probability distribution. And so what we have is this expression here, and so this phase integral just gives you the familiar modified Bessel function. And so unfortunately this you cannot do by hand, so you have to do it by a computer. So the first step is just generate a whole bunch of values for this function, and once you have evaluated this function at a whole set of values for theta that are of interest, then you can maximize this expression here to get the rate function for a whole bunch of values of the signal-to-noise ratio. Now the result of that analysis is the following. So what I'm plotting here is the rate function normalized by its Gaussian value. So if the central limit theorem were to work, so if you look at x equals 0, the rate function is equal to 1, as it must, because at x equals 0, the central limit theorem applies exactly. And this triangle point here is the point where our original detection threshold was set. And we see that at that point, the value of the normalized rate function is roughly 0.94. So what that number means is that you have to increase, in order to keep your rate of false alarms constant, you have to increase the value of your threshold by the square root of 1.06. So that's it's 1 plus this difference here. And so that turns out to be about 3%, which gives a value of the detection threshold of 14.4 sigma. So the fact that the Edgeworth series and large deviation theory give roughly the same answer here gives us confidence that at least that's the answer for that toy model. So in that simple case, the effect of the non-Gaussian tails are pretty small. Now, one problem with that earlier toy model is that it depends only on 2 parameters, so it's very far from what the real situation is. So in order to try to get closer to what the real situation might be like, the second step is to look at a more sophisticated model, which is essentially Newtonian chirp. So what we assume is that the waveform is generated from the quadrupole formula together with Newtonian equations of motion. And so this is like the Peters and Matthews waveforms. And we restrict attention to circular orbit only. So the functional form for the waveform that we use is this well-known formula. So here's the chirp mass. This is the distance to the binary. Well, that's the luminosity distance. Here's the gravitational wave frequency, and here's the initial random phase. Now, when you compute the overlap of 2 chirps in that model, so one is your search template, the other one is a given chirp that is your signal, what we use is the stationary phase approximation, which works pretty well because your chirps depend on only one single frequency. So they efficiently overlap only when the frequency of a given binary in the confusion noise matches the frequency of your search template. So that's when they cross in the time-frequency plane. And if they happen not to cross, then we just set the overlap to 0. And when they happen to cross, then the stationary phase approximation gives this result for the overlap between a template and a given Emery waveform. So here is just the usual weighting by the noise spectral density. This is the amplitudes of a given binary, the amplitude of your search template. This number here is the difference between the rate of change of the gravitational wave frequency between the template and the Emery when they cross, and here's the cosine of a random phase difference between these 2 signals at crossing. So this is the origin of the cosine of the random phase that we had in the original toy model. So basically that gives these variables some sort of random walk nature. So just to convince you that it's a good approximation to use the stationary phase, here's a simulation where a confusion noise data stream made of about 28,000 binaries and its overlap with a given search template is computed exactly by hands, and that's the green curve here. And the red curve, if you can actually see it, is the overlap predicted by the stationary phase approximation. And so we see that each curve, that the red curve follows the green one pretty well throughout a whole year of data. So there's some fluctuation.
The overlap builds up as a function of time.
Yeah, that's how the overlap builds up as function of time. Okay. So now to generate a given realization of the confusion noise, you have to pick out your binary parameters from some probability distributions. And what we do here is we use the following distribution. So for the supermassive black hole mass, the mass parameter comes from a distribution that is a power law where the power is m to the minus 7/24. For the small compact object mass, the distribution is just 1 over the small compact object mass. That's the redshift distribution, which I will come back to later. That's the original random phase distribution, and that's the initial frequency of the chirp. And this here is a threshold so that we can normalize this distribution. Now, where do these come from? Well, the masses and frequency probability distributions come from assuming that the rate of capture scales with the supermassive black hole masses m to the 3/8. So that comes from simulations. And we also assume that it's independent of the small compact object mass and of the frequency. So when you assume this scaling of the rate of captures, what you obtain is that the number of capture in a box around the values m and mu in mass parameter space, the number of capture per unit frequency, which is just the rate divided by omega dot, scales in that way. And just by construction of this quantity, the powers in each of these variables gives you what the power of your probability distribution must be so that this assumption is satisfied. So this is where each power comes from.
Where does the m to the 3/8 law come from?
I think it's from simulations. Just is it from Mark Freitag's simulation, or I forget where that comes from, but I think it comes from simulation. I mean, I know it comes from simulation, but I forget whose it is.
What's the capture mechanism? Because, for example, if it's a direct capture, it would scale as m to the 12 seventh, I think.
Oh well, yeah, that's possible. But it turns out that the actual power here, it matters very little for the final results. I don't want to spend too much time on discussing where that comes from. But
Earl had an argument on a big paper where it seemed, I can't remember if it was 3/8 or 1/2. It was something very close to that.
okay, and so the next point is, so there's some dependence on the redshift z in the mass probability distributions here in these bounds. So and these come from the fact that, well, the one contribution is from cosmological redshift, and that's just if you're using the standard formula for the gravitational waveform, then if it's located at some redshift z, you have to redshift both masses and the frequency, and then that gives you the correct formula for the gravitational waveform. And there's an extra contribution from the fact that the supermassive black holes grows in time because it's continuously capturing some compact objects. So the further the supermassive black hole is, the less, the smaller number of objects it has captured. So it's on average somewhat lighter than the closer supermassive black holes. Now for the redshift distribution, what we assume, we constructed assuming the three following things. So first of all, we assume that the relevant signals or supermassive black holes are all located within a volume bounded by a redshift of about 2. So again, this is because cosmological redshift would bring down all the waveforms below the Lisa band if your black hole is located further than that. The next assumption is we assume that the locally measured rate of capture scales like 1 plus e to the 0.6, which is roughly the square root of the age of the universe. And this scaling describes the fact that as the black hole swallows first the closest objects, it has to wait longer and longer for more objects to diffuse close to it in order for it to capture them. So if your black hole is further away, it's younger, then it's going to be capturing more objects. And finally, we assume that the locally measured density of supermassive black holes is independent of redshift. And when you combine these three assumptions, you obtain the probability distribution for the redshift. Okay, so now that we have that in hand, we have our second model. Now, if you do the Edgeworth analysis of that model, what you need, again, is the second and fourth cumulants, well, because the odd ones, again, vanish. Now, this is a much harder calculation because the dependence of the overlap on the binary parameters is much more complicated than it was in the first toy model. But still, you can compute the second cumulant fairly easily, but computing the fourth cumulant is a little bit more complicated because there's two divergences that you need to remove. One is due to the cutoff distance or redshift, which is the same as what I've discussed in the first toy model, but the other divergence comes from the fact that the stationary phase approximation fails in a region of parameter space where the masses and the frequency are very close to the ones of your search template. And what happens is that when you're in that region of parameter space, the delta f dot term that's here goes to 0, and so your overlap just blows up. But clearly in practice that does not happen. Your overlap stays finite, and so you just have essentially to cut out this little region of parameter space. And it turns out that the results for the fourth cumulant are actually fairly, well, in fact, very insensitive as to how you cut out this distribution. So you're pretty confident that the results are the correct ones when you do that. So the results of this calculation are the following. So the variance turns out to depend only on the initial frequency of your search template that way by this power law, and this is the Lisa bound, the lower bound of the Lisa band. And this is a result for the fourth cumulant, which again scales as 1 over your cutoff distance, and depends again on the template initial frequency, and here it also depends on the template chirp mass that way. Now these results both assume that the Lisa emission lifetime is longer than the template radiation reaction timescale, so that you see the whole Inspiral of your template within the Lisa emission lifetime. But if that's not the case, then you have to take that into account, and it turns out that when you do this, your result gets rescaled by this value where this is the Lisa emission lifetime, and that's the radiation reaction timescale of your chirp. So that's essentially the time it takes to go from your initial frequency all the way up to merger. Okay. Now, when you put these results in the Edgeworth series, that's what you obtain. And again, this scales as 1 over the number of binaries that are in your Lisa band. It has the following scalings with chirp mass and cutoff distance and template frequency. And for a number of MREs of order 10 to the 4, it turns out that the detection threshold must be adjusted to about 15 sigma in order for your rate of false alarm to be kept at the value that you desire. Now this is a correction that's a little bit more substantial than in the first toy model, but since the Edgeworth series worked reasonably okay for that toy model, I'm inclined to trust more or less that value, but I don't want to say that it's the correct one until we do the large deviation analysis. So this is what we need to still do. So we haven't done yet the large deviation analysis for that toy model. So we need to do that in order to confirm that the results of the Edgeworth series are good. And it would be good if we could find a different way to estimate the size of the correction terms that we generate by truncating the Edgeworth expansion just at 1 over n order. We have to make sure that this truncation is accurate at 15 sigma. And depending on these results, then we might decide to run a very large simulation with true waveforms that you generate from some kludge method, like what Stas Babak is doing at AEI, and then redo this problem with that probability distribution. But we don't know yet if that will be necessary or not. And this is all I had to talk about. So if you have any questions.